Hi everyone. Welcome to today's session on Kubernetes, a cutting-edge container orchestration platform. Whether you're preparing for an interview or looking to enhance your cloud-native skills, understanding Kubernetes is crucial. We'll explore its key features like automated rollouts, self-healing, and horizontal scaling. You'll learn about core concepts such as pods, services, and deployments. We'll also delve into Kubernetes architecture, covering both master and worker node components. This knowledge will empower you to manage containerized applications efficiently. By the end of this session, you'll have a solid foundation to tackle Kubernetes-related interview questions with confidence. Let's dive in and get started. Kubernetes Overview. Kubernetes, often abbreviated as Kubernetes, is an open-source container orchestration platform designed to automate the deployment, scaling, and operation of application containers across clusters of hosts. Developed by Google, Kubernetes is now maintained by the Cloud Native Computing Foundation, CNCF. Now we are going to see key features of Kubernetes. Some of the features are automated rollouts and rollbacks, self-healing, horizontal scaling, service discovery, load balancing, storage orchestration and batch execution. First and foremost, automated rollouts and rollbacks. Kubernetes can automatically roll out changes to your application or its configuration, and roll back changes in case of errors. Self-healing restarts containers that fail, replaces and reschedules containers when nodes die, and kills containers that don't respond to user-defined health checks. Horizontal scaling automatically scales applications up and down based on demand using the horizontal pod autoscaler. Service discovery and load balancing. Kubernetes can expose a container using the DNS name or using their own IP address. If traffic to a container is high, Kubernetes can load balance and distribute the network traffic so that the deployment is stable. Storage orchestration automatically mounts the storage system of your choice, whether from local storage, a public cloud provider such as GCP or AWS, or a network storage system like NFS or Ceph. Batch execution. Kubernetes manages batch and CI workloads, replacing containers that fail, if desired. Now, let's explore the core concepts of Kubernetes, such as clusters, nodes, pods, namespace and services, that form the foundation of this powerful tool. Cluster. A Kubernetes cluster consists of at least one master node and a number of worker nodes. Node. A node is a worker machine in Kubernetes, which can be a VM or a physical machine, depending on the cluster. Pod. The smallest and simplest Kubernetes object. A pod represents a set of running containers on your cluster. Service. An abstract way to expose an application running on a set of pods as a network service. Namespace. A way to divide cluster resources between multiple users, via resource quota. Now that we've covered the core concepts of Kubernetes, let's move on to its architecture. Understanding how Kubernetes is structured will help you grasp how it manages and orchestrates containers at scale. We'll look at the roles of the master and worker nodes and the various components that run on each. These include the API server, etcd, controller manager, scheduler on the master node, and kubelet, kubeproxy, and container runtime on the worker nodes. This architecture enables Kubernetes to maintain desired states, manage workloads, and ensure high availability. Let's break down each component and see how they work together to form a cohesive system. There are mainly two components. First one is master node component. Second one is worker node component. If we look at master node, we have API server, which serves the Kubernetes API. The Kubernetes API server is the central management entity that exposes the Kubernetes API. It serves as the front end for the Kubernetes control plane, handling RESTful requests to manage the cluster's state. All interactions with the cluster, including deploying applications and scaling services, go through the API. Next is etcd, a consistent and highly available key-value store used as Kubernetes backing store for all cluster data. etcd is a distributed key-value store used by Kubernetes to store all cluster data, ensuring consistency and reliability across the system. It holds the configuration data, state, and metadata of the cluster, serving as the backbone for Kubernetes high availability. As a highly available and consistent data store, etcd uses consensus algorithms to manage and replicate the data across multiple nodes. This ensures that the cluster state is preserved even in the event of node failures. etcd is critical for maintaining the desired state and overall health of the Kubernetes cluster. Next is Controller Manager. Controller Manager runs controller processes. The Kubernetes Controller Manager is a component of the master node responsible for maintaining the desired state of the cluster. It runs various controller processes, each responsible for different aspects of cluster management, such as node controllers, replication controllers, and endpoint controllers. These controllers continuously monitor the cluster state and make necessary adjustments to ensure the actual state matches the desired state defined by the user. The Controller Manager performs tasks like scaling applications, handling node failures, and managing updates. By automating these tasks, it ensures the cluster operates efficiently and reliably. Next is Scheduler. Scheduler. The Kubernetes Scheduler is a master node component responsible for assigning pods to nodes within the cluster. It watches for newly created pods with no assigned node and selects an appropriate node for them to run on based on resource availability, constraints, and policies. The scheduler ensures optimal distribution of workloads, considering factors like CPU and memory requirements, as well as affinity and anti-affinity rules. By efficiently allocating resources, it helps maintain cluster performance and balance. The scheduler plays a crucial role in managing workload distribution and resource utilization across the cluster. Now we are going to see Worker Node Components. Kubelet, an agent that runs on each node in the cluster, ensuring that containers are running in a pod. Ensuring that containers are running in a pod. It communicates with the Kubernetes API server to receive pod specifications and manages the lifecycle of containers according to the defined configuration. The kubelet monitors the state of pods and containers, reporting their status back to the master node. It also ensures that the containers are healthy and restarts them if they fail. By maintaining the desired state of the node, the kubelet is essential for the node's operation within the Kubernetes cluster. Kubeproxy, a network proxy that runs on each node, maintaining network rules on nodes. The Kubernetes Kubeproxy is a network component that runs on each worker node, managing network communication for the pods. It maintains network rules on nodes, allowing for seamless communication between pods and services within the cluster. Kubeproxy uses IPtables or IPVS to handle routing and load balancing for service requests, ensuring that traffic is efficiently distributed. It also facilitates the exposure of services to external clients by managing inbound and outbound network traffic. By providing these networking capabilities, Kubeproxy plays a crucial role in the connectivity and performance of the Kubernetes cluster. Container Runtime. The Kubernetes Container Runtime is the software responsible for running the containers on each node in the cluster. It interfaces with the kubelet to manage the lifecycle of containers according to the pod specifications. Popular container runtimes include Docker, Containered, and CRIO. The runtime handles the creation, starting, stopping, and deletion of containers, ensuring they operate as defined. By providing a standardized environment for container execution, the container runtime is essential for the consistent and reliable operation of applications within Kubernetes. Common use cases. Microservices architecture. Easily deploy and manage microservices, providing scalability and reliability. Kubernetes is widely used for deploying and managing microservices, allowing for scalable and resilient application architectures. Next, batch processing. It excels in handling batch processing and continuous integration/continuous deployment, CI/CD, workloads, automating job execution and resource management. Kubernetes supports hybrid and multi-cloud deployments, enabling applications to run seamlessly across different cloud environments and on-premises infrastructure. It also facilitates development and testing by providing consistent environments and easy scaling. Additionally, Kubernetes enhances high availability and disaster recovery strategies through automated failover and load balancing.